Welcome to the third part of the IBM SPSS Modeler demonstration series. We've already gone through data access and data manipulation. We've merged data sources and audited the data. Now, we're going to dive into analysis. IBM SPSS Modeler gives us the choice of a variety of pre-built algorithms to help create models visually and intuitively. Here we are in the modeling palette, where you can see the large number of available modeling nodes. Let's start over here on the left and talk about automated nodes. These are helpful for business users, especially if they're unsure which algorithms to use. Using automated techniques removes some of the guesswork and allows Modeler to arrive at a conclusion for us. Automated nodes can also help experienced data scientists to quickly compare several techniques. They compare a variety of algorithms appropriate to our data and determine which are likely to best predict our target variable. Sometimes, the best performance is achieved through an ensemble of several modeling techniques. Next, let's look at the subset of models under the heading Supervised Learning. We can use these algorithms to make predictions or forecasts based on historical data. Commonly used classification algorithms include decision trees, neural networks, support vector machines, Bayesian networks, and many others. Next, we have association modeling techniques. Think of a typical market basket analysis. For example, this would allow retail establishments to understand that customers who purchased product A are also likely to purchase product B. The a priori and karma algorithms are examples of association techniques. And finally, we have segmentation. We can group people or detect unusual patterns with automatic clustering, anomaly detection, and clustering neural network techniques. Premium users of Modeler also have access to SPSS text analytics, which allows us to analyze unstructured data alongside structured data using natural language processing. For this demo, we're looking at historical data to predict which telco customers are likely to switch to another provider, a behavior known as churn. The first thing that we need to build a model, of course, is a source of data. And in this case, we're going to use an SPSS statistics file that comes with Modeler in the demo folder. If we take a quick preview of the data, we'll see there are 41 fields describing each of our customers, and a churn field telling us whether or not the customer has changed to another provider. A 1 indicates that they did churn, and a 0 indicates that they did not. The next thing we'll do is go to the Field Ops palette and add a partition node and connect that up. What this does is splits our data randomly into training and test sets so that we can validate that our model will perform well on previously unseen data. Now, we'll add a type node. The type node has many uses in Modeler, but one of the things it does is allows us to specify the role of each variable in the model. We have all of the customer data as potential inputs, and the churn field is going to be our target. We discussed earlier how we could use the auto classifier node to select from a number of different classification models. But to simplify things for this demo, we're going to assume that we've settled on the CHADE model. CHADE is a widely used decision tree model. This pentagon-shaped node is what we use to specify the model characteristics and execute the building of the model. Here, we could specify such things as the depth of the tree, the stopping criteria, misclassification costs, and many other parameters. But let's just run it with the default values. We generate an executable model node shown by this golden nugget. Churn here indicates the model target. If we look inside that node, we can actually see a graph of predictor importance. We can also see what the decision criteria are. And in the CHADE model, there is a model viewer that allows us to traverse the tree and look at the various data splits and how the performance is going as we move down the tree. Now, if we put a table after our executable model and run that, we can see our model inputs and our known value of churn. We see that the model has added 2 new fields. $R churn is the model's prediction as to whether that customer will churn, and $RC churn is the confidence of that decision. Using the confidence can be very useful when deploying the model and determining where to set various thresholds. In the output palette, we can add an analysis node and run an analysis to look at the overall performance of our model. We see here that this model had 82% overall correctness on the training data and about 75% on the unseen test data. We can also go back to the Graphs palette and add in an evaluation node and that allows us to look at various types of charts. If we run the gains chart, we will see the lift we get from the model on both the training and the test sets. This concludes our demo of building a model with SPSS Modeler. There are many other analytics features available in Modeler. With time series forecasting, we can generate forecasts for one or more series over time with statistical modeling techniques. The time series node uses both exponential smoothing and ARIMA models. There's also a temporal causal modeling node that can provide insights into root causes of time-based behavior. We can extend Modeler with the R and Python programming languages to apply transformations and provide additional choices of algorithms. This can be useful if you've already developed a model or transformation technique in one of these languages. Extension nodes are available for import, transform, modeling, output, and export, and are found in the appropriate palettes. Here's an example of a simple logit model built with R. We enter the model building and model scoring syntax, which we might have developed and tested in an environment such as RStudio. When we run this model, we generate a modeling node, just as we did in our earlier CHADE demo. We can now connect this model to some test data and evaluate it. Modeler also allows you to incorporate extensions available in GitHub that employ Watson technologies and provide other valuable utility functions. These extensions can be accessed directly from the Extensions menu or from GitHub. The Modeler GUI also offers access to Python algorithms, so non-coding users can take advantage of the power of the Python language. These include high-performing XGBoost algorithms, single-class support vector machines, and the SMOTE algorithm for balancing data containing rare events. SPSS Modeler also offers advanced geospatial analytics tools for modeling and making predictions based on many types of location and time data. These include the geospatial source node, which can use shapefiles or a public map service, as well as the spatiotemporal prediction algorithm and space-time boxes. That's a quick look at some of the analytical tools in IBM SPSS Modeler. Now that we've built a predictive model, the next and final step is deployment, which we will cover in Part 4.